Record. I have to sneeze. False alarm. Hey guys, welcome to today's lecture. I will share my screen. So I'm going out of order. And the reason is this is like week 4 and I don't want to waste any more time. Not waste, but I don't want to take any more time with preliminaries. Even though we haven't covered Bayesian decision theory, which is pretty fundamental, but if there's time, I will cover it at some point. I may actually cover it informally as we go. I just don't want to dedicate a whole lecture to it before we cover the first learning algorithm. And so the first learning algorithm that you should learn, or I think you should learn, if not linear regression, is logistic regression. And I'm going to start with logistic regression, even though it probably logically should come after linear regression, just because many problems, a lot of the most interesting problems in machine learning can be formulated as a classification problem where the thing that you're trying to predict is discrete, and in this case binary. So that's the most common problem. And the other thing is that even in problems that have more than 2 classes, those can themselves be like you can model that, you can solve that rather as a set of binary problems. So if you have 3 classes, you can do 1 versus 3 or versus 1 versus 2, and then you can break down a multi-class problem into multiple two-way problems. And so what I want to do today is just show you, before we get into what I used to do previously, is start with the equations and then show you the code. But I'm going to do it backwards today, except that. Oh. Thank you. There's too many things. Record, share. Yeah, I'm old. Record, share screen, projector. Okay. Right. Thank you, though. That would have been bad. Right. Okay. So I'll just show this as like to formulate what the problem is. So I'm going to use this example, versions of this example throughout the course. So y is the thing that we're looking to predict. So in the most general sense, true state of the world. X is the information that you have available to estimate y with. So this is called the label or the target. This is called the feature or the data. Input, output for supervised learning. So in the brain scan example, our target variable is a decision on the health of the patient. So either the patient has a brain tumor or patient does not. And our input was, let's say, some MRI image, some MRI scan of the brain. We can take it to be 2-dimensional for the sake of this example, and we can break it up into pixels. And so, for example, if our brain scan only had 4 pixels, which it won't, but if it only had 4 pixels, the intensity of every pixel would be one of the features. And we would need to have some, to learn a model, you need to have something to learn from. I'm going to explain on the board in a second. It's going to be called a training set. So a training set is a collection of X and Y together. And in this case, it would be if you scanned a bunch of people and then also biopsied them or somehow found out whether at the time of the scan they actually had a brain tumor or not. And with that information, you would be able to learn the relationship between X and Y. And so first of all, just the general. Okay, so you have your data, and so your data can often be screen share. This actually worked relatively well when I watched the lecture, which I posted from last week. From the day that I plugged in here and had the camera on the board, it was pretty good. But I do have to make sure it's not flipped. You sure? Okay. Oh, on the computers, it's fine?
Maybe double flips it. I don't know.
It's too complicated for me to remember brains to figure it out. All right. Right, so what I mean by that is oftentimes you can arrange your data into kind of a table or a matrix. And so remember that, so this row dimension here will be the example dimension. So these are the training, well, I'm not going to call it training, I'm going to call them examples. Examples where you have X and Y. So this dimension here will be, let's just call them voxels, which is a three-dimensional pixel in a brain scan. And this here will be the truth. The truth as to whether the patient of that brain scan had a tumor. And so, you'll have a vector for every scan. You have a vector, and even if it's in a three-dimensional array, you can always flatten the arrays. So you'll have this long array for every patient that you have a scan for. And then you'll have, the first patient was healthy, the second patient ended up having a tumor. Respectively. And so what is often done in machine learning, so I mean, one approach would just be I'm going to construct small propaganda over here. So we want to construct some function of X that will predict Y, right? So there's a couple of things here, a couple of important considerations. One is that Y is binary, right? So if Y is binary, what does that mean about the nature of F? You think about the, so for example, what's the most general, like if you wanted to, like in machine learning, it's common to assume a family of functions, and then the learning algorithm has to pick one of those, one function from that family to model the data with. And so, for example, one family of functions would be, let me use G for this, would be all set of polynomials. I think a polynomial can pretty, and if you assume infinite degree, I think you can model every function. Function with it. So, for example, 0, 0, 1, 1. But this is a polynomial function. You can make the degree whatever you want, and you can synthesize any function basically without. It would not be a good idea. Polynomials are not very popular in machine learning, and the main reason is that or at least they are popular, but not beyond the linear count. One, it's not common to see quadratics do this, and the reason is that they just don't generalize well to new data, which is very important for machine learning. So, but yeah, I want to go back to my original question. Why is binary? Why is it either 0 or 1, right? So what does that say about the structure of F? What does F needs to have a feature here. And I wonder, for example, could F be just a purely linear function? I mean, it could be, but it wouldn't be a good idea, right? Because, for example, let's say that let's say you got a one-dimensional predictor. So why is it going to be 0 or 1? For X is just a one-dimensional scalar, and this will be a brain scan with 1 pixel. And so it would not a linear function of X would not be a good choice for trying to predict this, regardless of even if the relationship was super monotonic, right? Even if it was like this, it still would not be a good choice to approximate y with a y because y is discrete, and so there has to be some nonlinearity. There has to be something that saturates vertically. So, like if this is 1 and this is 0, we need F to return numbers that we need to always return 0 or 1. Really, and so the way to do that is something that is going to saturate, for example, large values of X and be floored at low values of X. So that's one thing that we're going to need, that logistic regression does for us. The second thing is, though, which is more important because it applies to all supervised learning, is how we use all of this data to learn our model. So we want to learn our function F, and we want to learn it to take these X's and produce these Y's. What's done in practice, and we'll have some demos in today's lecture, but future lectures, is that you do not use the entire data set at one time to learn your model function. What you will do is you will partition your data set into, the simplest case, 2 portions. And so a very standard partition is 1/3 to 2/3, 1/3. So this will be 2/3 that is going to be called the training set. And then this is the remaining third, which is called the test set. And so I guess my question to you is, why do we do this? Why don't I just use all the data to learn my function? I'm a radiologist, and I want to teach an algorithm to predict, to diagnose brain tumors from MRI brain images, and I have data from 1,000 patients. Should I use data from all 1,000 to learn my model? No, right? So why is that? Why would I hold out this data? Yeah,
And once you make your model, you have to build a test on something.
that's right. And so why can't I? But then why can't I test it on the same data?
I think it's automatically right because we already know this.
Yeah. So, right.
The oldest already has.
Oh yeah.
the-
So what you're saying though? Yeah. So So obviously in a real test set, you don't know what you don't know.
That's it, for
But
learning.
here, here in the test set, you do know. And so what is done in practice, by the way, is that there is a way to achieve both things: use all the data and still test your model on new examples, and that is to it's called cross validation. It's basically you start out with and the last there's a test set, but then you basically there's many combinations. So if this is 1,000 and this is 667, you can randomly select a different 667 examples on the next iteration to fit your model, and then so even though there is very many permutations, train test with for a large data set. Typically what's done is you break it up into like 5 portions or folds, and you'll take the first 4, train on the 5th, then take 1, 2, and 3, and 5, train on the 4th, etc. Then you have 5, estimates of performance. Also that way, if you do what's called k-fold cross-validation, every example has been in the test set once, which is nice. So that you use every example to evaluate your model once and only once. So, but I do have a question that I don't believe I've heard a good, satisfactory answer to. And credit to Professor Parra for many years ago raising this point to me. Why is it that in logistic regression, any machine learning algorithm, we do this? We train and test on in machine learning, the picture that you're probably used to seeing, I'll draw it. So if I have, in machine learning, you have, when the goal is to classify between, two classes, you see pictures like this, and you have a model that draws some decision boundary between the two classes, right? And it's you always, when you evaluate performance, you're always evaluating performance on so for example, maybe you'll get will quote you some accuracy. Let's say this will be accuracy of 100%, right? Test accuracy. But then notice anytime you look at like a linear regression figure, the picture you will see is something like you'll have your scatter plot, and then they will draw a line of best fit. Let's say your line of best fit is like that. And then you'll see something like R squared is 0.7. And that means that your model captures 70% of the variability in your data. But in this, the line, the slope of this line has been determined with the same data that is used to measure R squared. Common. This is a standard practice. So why is it that in linear regression, your y is now continuous? They do this. This is not test set R squared. This is training set. This is the same data that they use to fit this line is used to report the accuracy. But in logistic regression, you would get rejected automatically if you tried to do that. And so I actually think that the problem is that in linear regression, for some reason, everyone, it's just assumed. I don't know. Let me take a sip of my coffee and let you guys think if you can think of why do you think in linear regression, when you report R squared, you can use the same data as you used to fit your regression line, and why is that not true in classification? I have some ideas, but I've never actually heard a good answer. Any ideas? The only thing that I can think of is that in linear regression, at least the way, before kind of the renaissance of machine learning that we're in now, the amount of data that was the number of examples in the regression model was much bigger than the number of models, something like B naught plus B1 x. And like in the picture I've drawn here, E is just 1. We just have one dimension. The only thing I can think of is that in linear regression, the dimensionality is just very low. The number of examples is very high, so they just assume that that the performance is going to generalize by virtue of, it's a very simple model and it doesn't require a lot of data to fit. But I've definitely in my data seen examples where I've seen crazy things where you have, let's say you have 100 examples. You measure some line of regression. You measure some R squared. You take out just one example from your data set and you do it again and you get a significantly different value. So like I've seen those things happen. And so I am surprised that everyone's just still assumes that when you're doing regression. So again, I probably haven't defined regression classification, but all you need to know is that regression is predicting a continuous value, and classification, which is what we're talking about today, is predicting a discrete value. But for some reason, this is okay to do, but this would be completely this would be criticized swiftly if you were using the same data to fit this type of thing. Okay, so and for example, logistic regression, the algorithm we're covering today, does have a linear separation boundary, but more complex algorithms, you can have things like this. You can even have things like this. You can have very complex decision boundaries. What I'll say about logistic regression is that it should almost always be your baseline model. So when you practice machine learning, what you will do is when you first get your data, you'll just run it on like some standard out of the box algorithm and you'll see what you get. And the reason you do that is you want to get a sense of just the difficulty of the problem, like what's the signal to noise ratio. And then B, you want to know, you need to know what your baseline performance is so that when you go and, you know, when you architect and you know, whatever deep neural network model that you think is going to do well, you need to know what the benchmark performance should be. So if your logistic regression has an accuracy of 55%, then you will have very different expectations of your custom, you know, deep neural net than if your logistic regression has an 80% accuracy. And so the other thing about logistic regression that is great is that if you understand the math behind it, if you understand the theory behind it, then understanding the theory behind neural networks is very easy. There's really, it has the key characteristics of neural nets embedded in it. All right, so we have a healthy scan and we have a cancerous scan, and we want to figure out a mapping of the pixel values, the voxel values of the scan to predict Y. And so, as I said, this function f has to have a nonlinearity. If it's a linear function, we will not be able to produce a discrete target variable Y. And so what logistic regression does is it's really composed of two things. It's composed of a linear combination of your features. So in this case, a linear combination of the pixels plus what's called a static nonlinearity. So static in the sense that, so for example, you can be, it can be a step function. That'll be the easiest. And by the way, mathematically, you can write a step function as a hyperbolic tangent, for example. I think hyperbolic tangent was like the first nonlinearity that was used in neural nets. Now there's much more sophisticated nonlinear functions that are used. But the key thing is that, so you're going to take your x's and you're going to linearly combine them. And what that does, notice that now you've taken your vector features and you've mapped it to a scalar value. So what's inside those parentheses is now just a single number. And then that single number is then passed through some nonlinearity whose job it is to either output a 0 or a 1. Okay, and this is the key here. This is the most important part of the theory. And again, with all these algorithms that we're going to cover, it's always better to know what's in the box because it makes debugging easier. And so if you know what the algorithm, what's guiding the fitting of the algorithm, it's easier to diagnose performance issues. But in theory, and I'm sure that there are probably many people, there are probably many high school programmers that like do well on Kaggle competitions just by trying different algorithms without really understanding the math. And it's definitely not a prerequisite to have a deep intuition behind all the different learning algorithms. But I'm going to try to explain how we get this value. So I think, yeah, just switch to the board for a second. So we need something that takes, a real number and produces zeros and ones. Another way of viewing, by the way, what the learning algorithm is doing is to note that it's essentially, remember, we're trying to estimate the probability. probability of y, which is probably of cancer given this image, right? So a probabilistic view of classification is always helpful. So we want, and probabilities have to be between 0 and 1. And so if this is, we need, a logistic regression, the many learning algorithms assume that there's some kind of, if the features look one way, we have a probability of 1, and if the features look the opposite way, we have a probability of 0. So there has to be, sensibly, the algorithm has to start at 0 and end at 1. And it's that transition that's so important. The transition, first of all, the slope of that transition is important, and also the placement of that transition. So there's really the sigmoid really has two important parameters. One is when it hits 0.5. And the other thing is how quickly it goes from 0 to 1. And so intuitively, you know that as slow, this is, I think, it's helping me understand logistics. Something with a low slope means that you're not very confident. Right? It's a low confidence classifier. Something that abruptly moves from 0 to 1 quickly, that's like you have very clean data. You know exactly, the boundary between cancer and non-cancer. It's where it is, and you're confident, and you don't want to kind of hedge, because this zone here, this is the hedging zone, right? If you're like between 0.4 and 0.6, that's information for you. If your classifier outputs the probability of cancer is 0.51, that's a very different piece of information than if it outputs the probability of cancer is 0.99. Even though and I've skipped over Bayesian decision theory because I wanted to get to the core material today, but Bayesian decision theory says that from a minimum error standpoint, that the optimal decision rule in both cases is to say that it's cancer. But obviously, you should always look at the confidence of your model, and definitely in applications that some of the algorithms that I've worked on with companies, it's always a very important piece of information is what is the soft, it's called the soft decision, the x-axis here. The hard decision is like y is 0 or 1. The soft decision is what is it before you discretize it. And what I'm trying to get to is how do you map a real number from negative infinity to the probability of being 0 and 1. So consider this function here. So consider this, I call it g of u. So probably won't get to the math today, but maybe we will. This function, what are the bounds? Let me ask you guys, give myself a break, rest my vocal cords. What are the bounds of that function? U is a any real number. 0 and 1, right? So if you take u to be very, very negative, right? The numerator becomes 0, the denominator becomes 1, right? So we get the 0 that we want, and then if you take u to be very positive, the limit goes to 1, because the numerator and denominator become closer and closer to each other. So that is a really it seems to provide us with the tool that we want, right? Which is to map. U is gonna represent the cancerness of my pixels, and maybe that wasn't so PC. I have to cut that out. So if we divide through, right, by e to the u, and this is sigmoid has such, the logistic function has such lovely mathematical properties. But one of them is this, right? And then I think another property that this right is that 1 minus g of u ends up being this. No, I think it's let's just do that. Because it yeah, I don't want to, right? It's gonna be so their complements have this really, also this makes differentiating them, which we're going to need to optimize this when we do our gradient descent for this. It makes it really easy because 1 minus gu and g, 1 minus g and g have this really nice relationship. And so the important thing is that the thing that I'm hoping you can appreciate is that understand is that u here, which is the argument to our sigmoid, u here is just, it's just a combination of our inputs. So it's some weight multiplying the value of pixel 1. So u here is this linear combination of my pixels, and then right. So u, which is the input to our sigmoid, this is the thing that we need to arrange with 0 and 1, combines our data, and then we throw it into this. So you can think of this as kind of 2 steps. Step 1 is linearly combine the pixels, and step 2 is pass it to a nonlinearity, and then you have a prediction that is forced to range between 0 and 1, which is what we want. And not, so it achieves 2 things, right? It achieves that now you're closer to the you're bounded between 0 and 1, which is what you need because your y is either 0 or 1. And 2, it has a probabilistic interpretation. So if you W transpose X is exactly equal to 0, right? That's a question for you guys. So the radiologist runs a scan and W transpose X is exactly 0. What does that mean to him? What can he interpret from that scan? If W transpose X is exactly equal to 0. He takes his features, he already has his W built on past data. He runs it through, and W happens to be orthogonal to his patient scan. We know nothing, exactly. He should run a follow-up test because he's better off, he's just as good to guess at that point, right? So that's chance. And that's obviously not a good situation to be in. By the way, though, and this is something that they don't teach, at least I wasn't, in the lectures I've seen, in the classes I've taken, I've never had this communicated to me. I'll communicate it now because I may not remember later. One way of diagnosing overfitting in your model is if you run your model and you see that on every training example, the algorithm is giving you numbers that are either 0 and very close to 1, that's a sign of overfitting. You generally don't want that unless your data is like super clean and it's easy to separate, in which case, what are you doing? Like you're right. So that's like a really, I use that a lot whenever, so for example, even when you're doing what I said here, which is called cross validation, where I'm training on the first third and I'm testing on the last third, I will take the model, that I will take the coefficients that were learned from here and apply it to this data. I want to see, and that principle holds true for both. If the data is challenging, if I'm dealing with a problem like predicting cancer, where I'm not expecting, 99% performance, and I see that on the training set, it's every example is either mapped to 0 or 1, that's a red flag for me. That's like my model, there's no way it should be that confident. And so I work in one project, I work on a data set where the highest that we can ever expect to achieve is like 60%. If we get 60%, we'll be thrilled. And there, in that project, if I see that my algorithm is giving me 0.9 and 0.1 all the time, I know that's wrong. I know it's overfitting, basically. And by the way, if you get to that scenario, you either have to reduce the complexity of your data, or you have to collect more data. And this is kind of like the answer to every problem that you will encounter in machine learning is collect more data. More data will help you. Like even when the problem is, even when the stage that you're on is to allow your algorithm to learn efficiently with less data, and you're reading what's called hyperparameters. Even for that, the answer is get more data, tune your hyperparameters. So more data is often helpful, but sometimes, especially in biomedical field, which is important for you guys, in most biomedical problems, data is very expensive. Even like electronic health records, right? There just isn't in this space. There's no YouTube or Google image database where you have billions of examples available to you. And so this is going to be an important consideration. Is I think in machine learning for biomedical applications, the tools because all the textbooks are written, and not just the textbooks, like the field has really like the renaissance that we're going through now, the deep learning boom, has really come from computer vision and natural language processing. Both those fields just are loaded with abundant data. And so, I think an open question is how much we can take from, the advances that came from those fields and apply them to like the biomedical context, where our features are much noisier, and we just don't have as much data. And so that's very important. But yeah, more data will always look like a good solution to your problem. Okay. Right. So we'll do the demo on Wednesday. Today, what I'll do is just kind of try to give you some more intuition. So as I was saying, when your algorithm, the linear combination of your features works out to be exactly 0, it just means that you have no idea, and you're just a random guess will be just as good. On the other hand, if this inner product is very positive, the model's telling you that it's very confident that this is a cancer image. In the case where y is equal to 1 means cancer. If it's very negative, it means that it's very confident that it's a healthy image. And basically, what the model tries to do. Let me see if I have it right. So this is right. This is called the logit or log odds. This is very, very, if you read about machine learning online and blogs, tutorials, you'll often see this term log odds. So a ratio of probabilities. So let's see, these two numbers have to add up to be 1. And they're both positive. And so ratio of two positive numbers is always positive. However, and we don't like that. We don't like, in general, a lot of statistics is centered around, for example, Gaussian variables, where your variables can be positive or negative. And so we like that scenario. And so to convert the ratio of our probabilities into something that can be positive or negative, we take the log. And so, no, it's not really true. It can be negative, but actually, let me see. No, it's going to be, the log odds is going to, if this number is close to 0, this is going to be very negative. And if this number is, oh no, it is going to work. Oh no, it is going to work. My bad, I have to cut that up.
If it's greater than 1.
Yeah, if it's greater than 1, it's going to be it's a very large positive number, and the log of a very large number is another, it's a large number, but it's compressed. And if this is very close to 0, it's going to be the log of that is going to be a very large negative number. And so, and if you look at that curve now, right, if you look at the log odds versus p, now it's a little bit, the figure is a little bit vertically compressed, but you can kind of see that for a large part of that curve, it does look linear, which is nice, because now, you know, we can, yeah, so basically we're assuming a linear relationship between the log odds, and the log odds tell us, so if the log odds are, let's see, if, right, so if this number is bigger than, essentially, we're going to say cancer if this number is bigger than this number. So if this is greater than 1, then the log odds are positive. And if this number is smaller than this number, then the log odds are going to be negative. And so we have a nice mathematical framework for you know, for having a linear relationship between our data, which is our pixel intensities, and this now what the output needs to be, which is a binary probability. Let me just say, right. Notice that, and this is another thing that I spent quite a bit of time thinking about. Why is it? So really all we need to know is whether this is positive or negative, right? That's all we need to make our decision. So why do we bother? Why do we bother with the sigmoid? Like, why do we bother with the sigmoidal formula to begin with? If we can make our decision just based on a linear function of our data. But the reason we have the model is because the nature of W is super important, right? The coefficients of W are going to determine success or failure. If we choose them right, then if X comes from a cancerous brain, then the W's will produce a large number. And if they come from a healthy brain, they'll produce a small number. So, and we believe, and there's lots of empirical and theoretical evidence that enforcing the smooth transition and something that is monotonic with that score, which is what this model does, it enforces monotonicity in our model, right? So basically what I was saying is on an axis of which is like a measure of cancer-like appearance in the brain, there's this graded behavior that is produced by this model. And so you'll never, what it means is that if two images look alike, for example, in voxel space, this model will basically ensure that they will get mapped to a very similar prediction, which is not true, for example, for deep learning. There's all kinds of, and I have to go, but there's all kinds of examples. When we get to deep learning, I'll try to actually show you demonstrations of this, that you can, if you have a 10,000 pixel image, for example, and you just change the value of 1 pixel, all of a sudden the prediction of the neural network changes drastically, right? And and because it does not have this kind of behavior. But on the other hand, the trade-off is here. This can only learn pretty straightforward mappings between X and Y, but it's going to be robust. It's going to be robust to small variations in the input. Okay.
If you have the console, like the different folder, it's not static, right?
Well, it depends on your W. Like, no, I mean, it could. Like, if there are two regions, for example, where the cancer typically lies, both those regions will have a large weight vector.
So only that.
Only that, yeah. So you definitely assume, yeah. And that's why when we get to neural nets, what we'll see is that they have all these hidden nodes. Stop recording.